So we have been talking about entropy, and just to remind you of why we need to talk about entropy, the idea was that, so why do we need a second law? Or why do we need this concept of entropy? The reason was that if you look up at the first law of thermodynamics, that tells us that delta U is equal to delta Q plus delta W. Any process where the heat given to the system, delta Q, plus the work done on the system, delta W, is equal to the change in internal energy of the system, delta U, is allowed. Which means that if you looked at a process which had, so so you don't get confused by the sign. So let's say we had a process where 5 kilojoule was delta U and delta Q was minus 2 kilojoule and delta W was 7 kilojoule. Okay. So this is allowed by first law of thermodynamics. So as per first law, this is allowed. As per first law, however, this process is not allowed, right? Because delta U is not equal to delta Q plus delta W. The problem, however, is that if you take this first process over here and multiply everything with a minus sign and look at the reverse of the process, which is minus 5 kilojoule is equal to plus 2 kilojoule minus 7 kilojoule. As per the first law, this is still allowed. And you cannot distinguish, you cannot say whether this process is possible or not. However, as I made that analogy, that if you have, this could correspond to a ball dropping on the floor and gradually coming to rest versus a ball sucking the heat out of the ground and gradually starting to rise more and more. As per the first law, we cannot distinguish between both of these processes. And that's where the second law comes in. Second law says that we had three different statements. We had Clausius, Kelvin, and what is the name of the third one? Andrew, yeah, not Marco. Andrew's statement, right? And one of these said that you cannot have a process where the only net change is transferring heat from a cold body to a hot body, right? That's not going to happen. The other one said that you cannot have a process where you can just take heat out of a reservoir and completely change it into work. You must have some dissipation of heat. So I think it was Kelvin which said dissipation of heat. I will just write down the summary of the statements, not the full one. And Clausius said heat cannot go on its own from cold to hot. It cannot happen spontaneously. And the third statement was that a spontaneous process is one in which the total entropy of the system plus the surroundings increases. This total entropy is very important. And this introduced the concept of entropy without really defining it. So we took a step back and we defined entropy in two different ways. One, and we wanted it to be a state function. And the molecular definition is kind of more intuitive. The molecular definition says that entropy corresponds to increase in randomness of the system. And so for those of you who are late, I'm just doing a recap of what we have done before the midterm. So you haven't missed on anything. So the molecular definition says that S is equal to K log W, where W is the multiplicity or the number of ways of arranging a system. So if you have more ways of arranging a system, S will be higher. So as randomness increases, so there is fewer ways of arranging your exam. You can leave your exam over here. There are more ways of arranging exams all over, right? So the second state has more entropy. So this molecular definition is fine. It came later, but there is also a classical definition, which is what we are really going to use starting today, which says that, well, entropy is related to increase in randomness of the system. So it did not come by thinking about randomness, but you cannot think of it intuitively by seeing how it connects to the molecular definition. There is a more abstract proof of why these two definitions are equivalent. If anyone wants, send me a message, I will post it on Slack. But classical definition says that entropy corresponds to organized work changing into random motion, organized motion changing into random motion, right? Which is the natural state of everything. And we know that random motion is really coming from heat. It's not work. So it is going to be related to heat, but heat on its own is not a state function. So it turns out if you write down something like, if you look at the heat given to a system during a reversible process, on its own, that is a path function. But if you divide it by T, and if you integrate it, you get a state function. And this is what we are going to spend our time in understanding. So you can see why this is kind of related to randomness, right? Because it quantifies the heat given to a system. On its own, delta Q reversible is not a path, I'll come to you, a state function, but if you divide by temperature, it becomes a state function. Go ahead. Reversible. So if you calculate the heat given to a system during an irreversible process and then divide it by temperature, then you won't get the entropy change. Okay. So so which brings us to the next point. So if everyone okay with this before I go to the next page? Okay. By the way, after you have received your graded midterms, I'm going to do what's it called? Like an informal course evaluation, anonymous. I would really like to know what we should improve. What is it that you're unhappy with? It will be completely anonymous. I mean, we do those things at the end of the semester, but that's kind of pointless, right? I'm not going to probably see you again. So how will I improve in teaching you? So it's very important that you fill that up. You will get it sometime next week. The ones that you fill at the end of the semester matter for my promotion and things like that, which is of course also very important. But yeah, sure. Maybe one day I'll be the president of university, I don't know. But this feedback is even more important because if you tell me what can be changed now, and you can be mean in it, it's okay. I would really like to improve things, okay? So be nice in the end ones, but in this one you can be mean. Now, be honest in both. So the point here about this delta Q reversible by T being a state function is that if you think about pressure volume space, and let's say you have some point. So draw this diagram carefully. We are going to be spending some time with it. P1, T1, P1, V1, T1. And from this point, you are going to go to some other point which has the same temperature, but different pressure and volume, okay? P2, V2, T2. So you can have different paths connecting these 2 points, right? Let's construct a path A that goes isothermally. So in this one, I don't want to call T2, I want to call it T1. The temperature is kept the same, okay? So path A is isothermal reversible change. So we are talking only about irreversible change. Of course, even path A could have different variants of it. Even path A, you could do isothermally, but in a different number of irreversible manners. We are not interested in those. We will be talking about irreversibility because entropy allows us to distinguish irreversibility from reversibility. And which is a good point to write down over here, that delta S total positive is a spontaneous process. Delta S total negative means reverse is spontaneous. The process that you're looking at, that's not spontaneous, but its opposite process is indeed spontaneous. And delta S total is equal to 0 is a reversible process, which means the front process and the forwards process and the backwards process, both are spontaneous, okay? If you came, those who came late, please leave your midterm over here. And if you haven't picked up your homeworks from previous times, they're over there. So let's consider a path A, which is an isothermal reversible change. But this is not the only way to go from point 1 to point 2. Can you think of other ways? You saw it in one of the practice problems. Anyone remembers? Go ahead. Adiabatic and then raise the temperature isochorically, right? It's just one way. You could imagine many other ways. There is nothing super fantastic about this. So the second way would be we go adiabatically. And you all looked at it in the practice problem as to why is an adiabatic curve below the isothermal curve, right? You worked through it. The slope of this one is sharper. And then you go isothermally. So let's call this part as B and this part as C. And let me draw arrows because it really matters which direction we are going in. Otherwise, it's all different. So we'll draw arrows. So path B plus C is adiabatic change from P1, V1, T1 to some P3, T2. What should be the volume at C at this point at the bottom? V2, right? It is the same as the one above. So this volume is V2 to P3, V2, T2, and isochoric. Then you keep the volume constant from P3, V2, T2 to T2, V2, T1. So the symbols, the subscripts are super important. Otherwise, everything will get messed up. So you can see these are two different paths. And if you want, as those of you who always ask me, how to do more practice problems, this is a simple practice problem. Calculate the heat change along both of them. We will be doing something similar. We will be calculating entropy change. And I will show you that the entropy change using this formula of Q reversible by T is the same for both these paths. But you can calculate the heat change and see that it is not the same. And we can think of a third path here, which was also there in that practice problem, which is you go over here isobarically, right? You keep the same pressure and move along a curve D, and then you do isochoric compression, E. What is isochoric compression? No, you do isochoric change. Isochorically, you change from this point over here to the bottom. So this point, what will be the pressure? What will be the volume? What will be the temperature? Can we say anything about the temperature? We cannot, right? It's going to be something different. So let's call it T3. It's yet another temperature. So path D plus E is isobaric plus isochoric. Now, is T3 going to be higher than T1? Oh, one important thing. We are going to do all of this for an ideal gas. We are going to illustrate all of this for an ideal gas. So what we are doing right now is to construct a bunch of different paths for an ideal gas. So it's better to write it. I should have left some space. Ideal gas illustration Y delta Q reversible by temperature is state function. So we are not giving a full proof. We will be working through a full proof of why it is a state function, not just for these paths, but for any paths, and not just for an ideal gas, but for any gas. But I'm trying to show you as to why this works. Also, this makes lots of nice problems by working through cycles like this. I have posted a video link to Khan Academy's cycles, pressure volume cycles. Please go through that video. He has a lot of good, he will give you more intuition than you get in. I hope you get enough intuition here, but if it's not clear, please go through his videos too. So assuming it's an ideal gas, will T3 be smaller than T1 or higher than T1? Why? E and V are both bigger, right? V is same. Yeah. So what he said is that since it's an ideal gas, PV is equal to nRT, right? And at this point over here and this point over here, we know T is equal to PV by nR. And we know volume is the same, right? V2 and V2 are the same. But we clearly see that P1 is more than P2. Therefore, the temperature at T3 is going to be more than T1. So this thing that we just drew is isochoric cooling. It's not isochoric heating. So the question is the entropy change delta S along path A equal to the entropy change along path B plus C, and is that equal to the entropy change along path D plus E? If we prove this, this is not a proof that indeed entropy is always a state function. This is an illustration that entropy might be a state function for these different paths for an ideal gas. Okay, this is just to get some intuition. We will be doing a full proof later. So I am going to do this part today. We will do this. This part, that B plus C is equal to D plus E, is your practice problem. How many practice problems did we post? 4 or 5? 4? Let's call this 5. Okay. So once I work through the proof for A and B plus C, I would like you to go back and think yourself about how to show that B plus C have the same entropy change as D plus E. Anything involving B is very easy. What is the entropy change along path B? Using this formula. Why? It's an adiabatic process, right? So life is very simple. So some of it is simple. Anytime you see an adiabatic and you have to if you have to calculate entropy, always think in terms of adiabats, because your life becomes very simple. Heat reversible change is 0, so nothing to calculate. But let's work through it carefully. Let's first look at path A. So I'm going to draw this picture if I can find chalk. You see chalk? Anyone see chalk? Jeff Davis told me there's chalk here. I can't find chalk. Make sure you have copied this picture. We will be referring to it again and again. That's sad. There's some chalk here. So I'll draw it here for your reference. This is pressure. This is volume. P1, V1, P1, P3, V2, P2. This one is an adiabat. Over here we have an isotherm. That's A. This is B. This is C. And then we have these two. This was D. This was E. So this is E2, V2, 1. And this is P1, same pressure, same volume, V2, and a higher temperature, P3. And this is all, we are doing this, all of this for an ideal gas and reversible paths. Okay, refer to this. So let's go ahead. Let's try to calculate the entropy change along path A. Delta SA. How should we proceed? I want you to all to help me and work on this. What should be the starting point? We are not using molecular definition, we are using classical definition. Go ahead. First, let's write down the formula for entropy, right? Entropy, not Q. So this is delta Q reversible divided by temperature along path A, right? So anytime you do any of these problems, I always recommend start with the most basic formula you can write. So for entropy, just start with the definition. And so in this case, you could start with first law, but it might trip you. It's better to write this. The reason it is better to write this is because what happens to temperature during the process A? It does not change. So we can get the 1 over T outside, right? So that's quite nice. So for this case, it will be 1 over T1 delta Q reversible. Now we can talk about the first law of thermodynamics. We know that du is equal to delta Q reversible plus delta W reversible. What can we say about du for an isothermal process for an ideal gas? Everyone's favorite, it's zero, right? The thing you always want to say, but you never get a chance because it's never ideal. Here it is. So this is equal to zero. Again, why? Because this is ideal and this is isothermal. If it was not ideal, we are screwed. We can't do that. Turns out, even if it was not ideal, the entropy change along A and B plus C will still be the same, but this proof won't apply. And for that, we have to see the complicated proof involving the Carnot cycle. So this means that delta Q reversible is equal to minus delta W reversible. What should we do next? Any ideas? Go ahead. PDV. So what should be the sign here? It's minus PDV. Work is minus PDV, right? So minus multiplied by minus becomes plus PDV. And we can simply write P. Why don't we have to write P external? Anyone else? Go ahead. It's a reversible process, right? Otherwise, so it's PDV. So now we have delta SA is equal to 1 by T1 integral PDV. What should we do next? Go ahead. Correct. Let's try that. Well, I don't know if it's correct. Let's try it and see what happens. So you said NR, and what should be the temperature be? nRT by V. But do we know anything about the temperature? Along path A? It's the same. It's T1. It's the same. So the nice thing is, even if we had not taken the T1 out, it would have canceled internally inside, which is super nice. So then this, and why did we write T1 here? Because of path A. You could not do this along any other path. We have doing this for path A. Okay. So then this thing becomes NR can totally go out of the integral, no problem. dV by V. And what are the limits on the volume? V1 to V2, right? Initial to final. So what is the number? NR ln V2 by V1. Have we seen this before? We did this, right? So we just redid that derivation. Okay. And this simple derivation will show up again and again and again. It better become second nature. So we got delta S along A. Let's call this as equation number 1. Now we have to think about delta S along B plus C. So we still don't know whether it is a path function or a state function, but we can write it down as the entropy calculated along path B plus the entropy calculated along path C. B is an adiabat. What is the entropy along path B? 0. Great. One of these just goes to 0. Delta S B is equal to 0 because it's an adiabat. This would have been true even for a non-ideal gas, right? Adiabats delta Q reversible is equal to 0, period. Ideal, non-ideal, doesn't matter, it's 0. We have to now think about delta SC, and that's interesting. Let's work through it. How should we proceed with delta SC? Again, let's write down the same formula that we did last time. Integral of delta Q reversible by temperature. What type of path is C? Isochoric path. So for an isochoric path, for a constant volume path, what do we know about the heat change? All right, you answered many already. Anyone else? Sorry. You also answered. Anyone else? I want to make new friends. So. Andrew has also been answering a lot of questions. I want someone else who I can give a name for a theorem. Sorry, Andrew. If no one else, then we go back to Andrew. Okay? Maybe. Okay, Andrew, what do you think? Okay. That's all correct. You're both correct. But I'm looking for heat capacity. Can we express it in terms of a heat capacity if it's a constant volume process?
Yes.
CV dt, right? That's always true. Even that is true for non-ideal gas, right? You don't have to do anything. So it's a constant volume process. So this is going to be CV dt. And why am I so happy about writing down? So happy that the screen went over, sorry. Why am I, once it comes back, let me have my coffee. Why am I so happy about this equation? Go ahead. If it was independent of temperature, I could take it out. But the nice thing is that this third equation is state dependent. It does not depend on path. It's just dt. While the middle one has a path dependence, right? The nice thing about CV is that CV does not depend on what state you're in, even if it's dependent on temperature. Yeah, if you just assume a simple model for CV, you could take it out. But even if CV was dependent on temperature, it does not depend on the path. So we have been able to transform delta Q reversible essentially by using what both of you said, that dW is equal to 0, we have been able to change it to CVDT. So, and what is the limit of temperature here? Temperature goes from T2 to T1. So we have to be careful really about the sign of the limits of the integral. So, and I want to emphasize that the CV can depend on temperature. I'm not assuming that CV is independent of temperature. But it's an ideal gas, right? So if we had a non-ideal gas, we could proceed from here and think about how CV depends on temperature. It's an ideal gas. So can we do better in calculating this thing? Can we put down an expression for it? Any ideas how to proceed from here? People who have answered before can also answer. It's okay. If it's an ideal gas, what do we do here? Think, keep thinking. Go ahead. 3/2 an hour. Yeah. I want to express this in terms of the volume. How do I change this integral to something that depends on V2 by V1? Think through it. Go ahead. Maybe. I want everyone to take 1 minute to think through it. So I will write down the expression that I'm trying to look for, which you kind of expect what you want to see, right? We want to show that delta SB plus C is the same as delta SA. So what I'm trying to show here is that this thing will be the same as NR ln V2 by V1. How do I get to that? Because if we could show this, then you can see that delta SC is equal to this much, delta SB is equal to 0, and delta SA was equal to this much too, right? So we have shown that delta SA is delta SB plus delta SC. So how do we, this is what we want to show. If this was an exam problem, this is where you would be stuck. And some of you would put in some random thermodynamics in the middle and try to trick me. It happens every time. And I'm like, wait, maybe the student does have a point here. So how do we do this? Let me go to the next page and then we will work through this. Anyone can see the full pathway to do this? Are you confident? You are saying CV dt is equal to for an ideal gas. And then is equal to what? But delta Q, why are you ignoring that? You cannot say this is equal to this, right? Right? That's not true. So that doesn't work. You have to scratch that. Any ideas? I'm stuck. I need help. Okay, it's not trivial apart from here. It's just algebra, but it's slightly complicated. Let's work through it. We want to look at, let's consider CVDT. Okay. This is the expression we want to manipulate. And remember, all of this we are doing for an ideal gas. If it was non-ideal, we are done. This proof won't work. We will have to use the more general proof we do later. For an ideal gas, what can we say? PV is equal to nRT, right? We know that, no problems, no questions asked, that's always true. Therefore, pressure is equal to nRT by volume. So what's your name in the middle? Huh? Justin. So Justin, you were almost on the right track. Okay, we have to work. You had the right idea. Let's work through that. So Justin was telling us that we have du is equal to delta Q plus delta W, right? And will this, let's see, what's the least confusing way to do this? Okay, now I remember. So what we want to show, the reason why this proof is complicated, we want to show that something involving change from this point to this point can be expressed as the difference, as the ratio of volumes V2 by V1, right? V1 doesn't even show up over here. That's what makes it very complicated. If you just try to focus on this path over here, you will never get this proof. It just won't happen. We want to connect T1 and T2 with V1 and V2. That's not happening along this path. There is, however, one path where it is happening. You see where? Along the adiabat. Along the adiabat, V1 T1 is changing to V2 T2. So in order to prove this relation, we have to actually go and look at the adiabat. And that's what makes this so tricky. Okay? So it's a bit like, at least some of you in the back look like, what are you talking about? I hear you. This is terrible. You cannot just prove this. The first time I taught this class, I got totally tripped. I was like, how do I do this? I just can't do this. Then I realized later, in order to do this, there is no V1 here. How are you going to do this, right? And if you don't, and why do we want to do this? Because we can see that is the light at the end of the tunnel, right? If we can show that is to be true, then we have indeed shown that delta SA is equal to delta SB plus delta SC. But in order to do this, we have to think about something else. So let's go back. To do this, let's go back to the adiabat. which is path B. Along the adiabat, we can use what Justin was saying, right? We can say du is equal to delta Q plus delta W. It's an adiabat, so delta Q is equal to 0, right? And delta W becomes minus PdV. It is also an ideal gas. So du is equal to CV dt, right? I have been telling you this many, many times. Hopefully all of you remember it, that du is equal to CV dt for ideal gas. Therefore, CV dt is equal to minus PdV for ideal gas adiabat. Okay, this is not true for path C. It is, however, true for path B, that CV dt is equal to minus PdV. Now we can say CV dt, and we can use in the ideal gas law, which is PV is equal to nRT, and this becomes nRT by V multiplied by dV. The temperature we bring to the left side, CV by T dt is equal to minus nR dV by V. Now, do you see how those two might be connected, right? And by looking at this adiabat, we therefore get that CV by T dt going from, and where are we going? We are going from T1 to T2. T1 to T2 is equal to minus nR dV by V, and the signs are very important. V1 to V2 are the limits of the integral, V1 to V2. But if you look at equation number 2, what is the limit of the integral? It's not T1 to T2, it's T2 to T1, right? Therefore, T2 to T1, CV dt by T is equal to plus nR V1 by V2 dV by V. Oh, sorry about that. V1 to V2, let it come back. Which is nR ln V2 by V1. QED, which is fancy way for saying, I got this. Quad error demonstratum or something like that, QED. So it was a tricky proof, right? No wonder any of you were able to think it through. Justin had the right idea, but that equation did not really apply to the isotherm, right? We had to go to the adiabat and get the same integral that we were looking for coming out of the adiabat, and then just flip the sign and see we got the same thing. So go through this page 4 many, many times. Try to do this on your own. I still get tripped. It's not trivial. I come here and I say, okay, I have to prove this now. And what you have to remember, in order to prove this, you have to go and look at the adiabat. And we could do things like this because we are in the wonderful land of state functions. CV is a state function. If CV was a path function, we couldn't do this, right? We would have to be like, no, we can't go to the adiabat. So you can derive properties for different processes and apply it to some other process. And you can immediately see why this is useful, why this is kind of what makes thermodynamics very useful. You could be designing one experiment under one control condition and talk about another experiment, another control condition, as long as you're interested in change in state functions, right? Of course, thermodynamics assumes reversible change. What we have done so far, it assumes things in equilibrium, which is not always true. That's when it starts to break down. So what have we shown then? Therefore, we showed that delta SA is plus nR ln V2 by V1, right? We showed that over here, delta SA is equal to plus nR ln V2 by V1. And we showed that delta SB plus delta SC is equal to 0 plus delta SC, which is also equal to plus nR ln V2 by V1. So we have just showed that for ideal gas, we have not proved it for a non-ideal gas. We have not proved it for other paths in general. For your practice problem 5, I would like you to go and show that this is the same as delta S D plus E. For E, again, you might have to use some tricks. I think this part is easier than actually doing what we did, but please work through it. Please don't look up any notes. Try to do it on your own. Show that delta SB plus C is equal to delta SD plus E, which we already know is equal to delta SA. So then we have completed this illustration that in order to go from this path over here to this path over here, you can take path A, or you can go B plus C, or you can go D plus E. The entropy changes by the same amount, which is kind of an illustration for why all three paths have same delta S. This is not a proof. Once you have, some of you, my rule is 5 students should have posted a solution to this. Once you do that, after that, we will move next class to something called Carnot cycle, which will allow us to prove that entropy is a state function for any path, any material. And this is going to be a 3-step process. We will construct a very special cycle called the Carnot cycle, which looks like something like this. It's got adiabats and it's got isotherms. And we will show that along this cycle, delta S ideal along Carnot cycle, this very special cycle is equal to 0. So if you start from here, from point A, and you go to B, and you go to C, and you go to D, and you come back to point A, along Carnot cycle, an ideal gas has entropy change equal to 0. This will be our first step. The second step, we will prove that delta S Carnot, any gas is equal to 0. We will use this proof, the first proof, to show that actually it is true, not just for ideal, for anything. And then we will go to delta S, any cycle, any gas is equal to 0. And it will take us a lecture or two to prove this.